Hello, this tutorial is about the adiabatic quench calculation, which is the newest calculation in our calculation set. What we'll first do in this tutorial is tell you how it works and what it's based on, because that's important to understand the results later. And therefore I have a simple model open here already with an adiabatic quench calculation, or at least part of it already implemented. And here in the first tooltip of the adiabatic quench calculation, you'll see a few equations which are used to solve the change in temperature and the change in current in case a superconducting coil in your model would quench adiabatically, which is important to stress here because there's no heat transfer from anywhere in the model to anywhere else in the model. So there will be changes in temperature, but this heat that is formed during the change of temperature doesn't go anywhere else. So if one piece of the coil would heat up, it doesn't actually also heat up a different piece of the coil. So that's important when you look at the results later on. What it does in this calculation, it solves for three equations. 2 for change in temperature and 1 for change in current. The first change in temperature is a change of the hotspot, basically the temperature change of the hotspot, where you basically take the power dissipation in the hotspot and divide it by the heat capacity. That's how you get the change in temperature for the hotspot. The other change in temperature is for the whole coil. So basically there's the rest of the coil, and the temperature change in that coil is estimated by the power dissipation in the rest of the coil divided by its heat capacity. And finally, there is change of current, which is basically calculated by the inverse of the inductance matrix, Mij, times the voltage. And the voltage here is basically current times resistance, which is normal ohm voltage. This voltage in the last equation can arise either because of the normal zone that is starting to appear. So when the coil quenches, it becomes normal conducting, and then it has a resistance and therefore a voltage. So this is a very tiny voltage usually. Now, before you start any quench calculation, it's important to understand that in order for the quench calculation to even work, you need to know the material properties. And therefore, you have to add material properties to all the pieces in your model. For now, I'm going to disable this support cylinder. We're just going to look at a solenoid here. And let's assume that it's LTS conductor. So it's in that case, we can select, for instance, from the list of materials, we can select niobium titanium wire. And if we look at the material properties, you can set here all kinds of things. For instance, the wire diameter or the normal conductor to superconductor ratio. Those two are used to calculate the fractions of the materials in this composite material. So it's not used later on to determine the conductor size in the end. So as long as you got here a proper diameter and the right amount of superconductor to normal conductor ratio, these fractions here will be calculated, and that's just used for material properties. Material properties are needed for the normal zone propagation velocity, for instance, resistivity, all that kind of stuff. That's needed to calculate the result of your adiabatic quench calculation. If you look later on, if you want to know how Rat interprets the conductor size or the cable size, that's basically the area that you have, your cross section of your model, divided by the number of turns. So that's how it uses how it takes the conductor area. So this can be, in principle, I can also make this everything twice as big, 1.9, and this 3.8. Of course, it's not going to work. In principle, the fraction is always the same. So in principle, I can make here whatever I want, but as long as this fraction is used here, this is always going to be the right fraction. So it's averaged materials properties. Now, once you've added the material properties to your model, you can start setting up the quench calculation. And as for all calculations, you right-click on the calculations tree add calculation, and then at the bottom of the list there is the adiabatic quench. I've already added it here, and then there is a few calculation settings. First of all, the adiabatic quench has stop conditions. If one of the 3 stop conditions is valid, then the calculation stops, because it's not useful to continue after one of these criteria have reached. For instance, if you reach a certain time, so if you only want to simulate like 10 seconds, then this is one of the stop criteria. Or if one thing in your model, for either the hotspot temperature or the coil temperature, reaches 1000 Kelvin, but maybe even 500 Kelvin is already like enough. It's not necessary anymore to solve afterwards. Or the last criterion is once every object in your coil reaches a current percentage of its original current that is lower than what you set over here, because in case of most case of the current, it's exponential, so it will continue to decrease forever, basically. So that's why you can have this as a stop criterion. Then there's also some integration tolerances, which have to do with how the differential equations are solved. And if you're, I think in most cases you don't need to touch this, but if you need a bit more accuracy, then you can play with these values and see if it gives you a better result. But it's an adiabatic quench simulation. It's not necessary usually to play with these. So now we're gonna play with a few different cases that you can simulate using this adiabatic quench simulation, but therefore it's first important to add a circuit to the calculation, and we need a so-called protection circuit for the adiabatic quench calculation. In the protection circuit, first of all, you have the powering, and this powers the coil or coils with the circuit ID 1. So let's go to our solenoid. Here we have indeed circuit ID 1. So in this case, this will power the solenoid to 2000 amps, or let's do 1000 amps, doesn't really matter. You can select a drive here from the list. For instance, if in case you want to have like a sine wave as a current, then you can select that here as well. But here we, for simplicity reasons and for this tutorial, we'll just do a direct current drive of 1000 amps. So the coil is charged to 1000 amps. And then we go and look into the quench detection. So this is for powering. The next set of settings is quench detection. So this is based on voltage. So it's assuming in this model that in one way or another, you're able to measure the voltage of your coil. And then you can choose a voltage threshold at which you define that there has been a quench and you want to you want to start protecting your coil against quench. So here, let's do a voltage threshold of 0.1 volts. That should be fine. And then there is a delay which is associated with the detection. And this delay can be caused by your signal processing, for instance, because you probably have a high pass filter or a low pass filter or whatever kind of filter to filter out the noise in your voltage measurement. Otherwise, you'll be discharging your coil very, very often if you have a bit of a noisy signal. And this signal processing time, it has a finite time associated to it. So this is basically the amount of time needed to process your signal before you actually activate your quench protection. Let's go to the most simple case first. And that is when after you have detected a quench, you switch in an extraction resistor or a dump resistor. And that's here in the next bit. This is called energy extraction. And let's first set, so there you can also use a resistor, but that's the next case. So let's first look at when we have just a normal resistor that is switched in series with your coil after your quench has been detected and your signal processing delay has passed. In that case, you basically need a physical switch as well in your real life coil. And again, it takes a certain amount of time to open the switch. And this switching time you can also set here. If you want to include this in your detection delay, that's also fine. In that case, you put this to 0. and you put this to 0.06, then you have the same result, because basically what happens is in this adiabatic quench calculation, your resistor is switched in series with the coil after T delay plus T switch. So if you want to separate them or not, that's not so important, but in the end, adding the two together is the time when your switch is opened. So the next value that you can set is basically the voltage over your resistor after it's switched in, and it takes the current over the resistor to then calculate the resistance of the resistor through Ohm's law, because it's just a normal resistor. This current has to be the same as the current in your power supply. Well, it doesn't, but actually if it's easier to understand the results if they are the same, because now if I set this to 100 volts, it will be easy to see basically the 100 volts after the resistor has been switched in. So let's make this into 0.03 and this as well. Oops. Because then you will see also a nice feature of the detection delay in the switch time. So once you're happy, you can click calculate, and then obviously the calculation starts. And it shows the results in a plot that you see over here. And all the data is in one plot. So the change in current, the hotspot temperature, and also the voltage and detection time. So let's first look at that. So if I scroll, oh, actually, this is the current axis. So I'm gonna put it on the opposite side, and I'm gonna also put the voltage on the opposite side, because then it shows up here. And I'm gonna zoom in. I can scroll and then I'll zoom in. To show you what happens in the beginning. So we set a protection voltage, or detection voltage, excuse me, at 0.1 volts. So that's over here. And then I made this not out to fit, so then I can also zoom in on the time axis, because everything happens quite fast. All right. So here we have our voltage reached. Whoop. Then our 0.03 seconds are our detection delay are happening, which is basically this time over here. So at this time our switch is opening, but our switch also needs 0.03 seconds to open, and that's what you see over here. So this is 0.03, and from the 0.1 volts to our detection time is also 0.03. Now I double click on the axis so that I zoom out one more time. And you see that as soon as the switch is switched in, you have this 100 volts that we set over here. That was the voltage on, over here. That's the voltage on from the resistor that's used to calculate the resistance in the end. Now let's look at the current and the hotspot temperature. I will move back the axis of the voltage again. Voltage to the opposite side. So, and I'll whoop. So we started at 1000 amps over here, and this let's show the detection time. So this is when it was detected, and that's when the switch switched in. And you see that you get this exponential decay because it's an RL circuit basically, and your temperature also starts to rise because you have a normal zone developing. So this is your hotspot temperature. It starts to rise, but as soon as there's less and less current, in fact there's no more current, the temperature sort of stabilizes at slightly above 60 Kelvin. And that's what you see here. Now, because this is external extraction, so the resistor is receiving all the energy, all the stored magnetic energy is dumped into the resistor. The coil temperature doesn't change in this adiabatic quench calculation because there's no heat transfer. So the heat from the hotspot is not transferred to the rest of the coil, and that's why that coil doesn't change in temperature, and that's why the temperature of the coil is not shown in this plot. If you have a different scenario, which we will see later, the coil temperature will change, for instance in the case where you have heaters, quench heaters, and then the coil temperature will be in this plot as well. Now for the next case that we're going to look at, I'm going to leave this case open because the next case will be the use of a varistor. So it's again external extraction, but what a varistor does, instead of having a linear dependence of the voltage on the current, it has this dependence. So the voltage of a varistor is a constant times the current to the power beta, and beta is a material property of the varistor. And this C is basically the amount of voltage at 1 amp, but that's calculated, this C, based on these values. So if you again have a voltage of 100 volts at 1 kiloamp, and you set this beta to 0.42, it will then calculate this C factor for you. This 0.42 is a material property of a specific varistor that we use. But you can set your own beta value there if you know a different value. So again, this is external extraction, so the coil itself won't heat up. But what happens, the voltage stays high for longer. So here you see there's a peak in the voltage and it quickly goes back to zero. But in the case of a varistor, the voltage will be high for longer, and therefore the extraction will be slightly faster. And because the extraction is slightly faster, usually the hotspot temperature will be slightly lower. And that's what you see over here. So if you look at the voltage now, here I clearly zoomed in differently. So let's here auto fit, and this also goes to 2.5. Oh, excuse me, 2.5. Yeah, obviously that's not in the plot here because that's where the plot stopped. So let's do auto fit, and let's zoom in on the axis here on about the same time scale, more or less. There you go. You see here you have sort of a linear rise, but here the voltage stays high for longer. And if you then look at the hotspot temperature, here it's slightly above 60 and here is below 60. And the current will also decay faster. In the same time, you have less current in the coil than when you would use a resistor. So the top case was for the case of a resistor and the bottom case of a varistor. And the voltage for the two was kept the same, so you can actually compare the two cases. Another quench protection method is by not dumping the energy outside the coil in a dump resistor, but by dumping the energy internally. And in that case, we have another checkbox here saying use internal dump. And then as soon as the switch is opened, you will not see that the energy goes into a dump resistor, but all the energy that would go in the dump resistor now goes into the coil. So we check the internal dump, and now you see that there is a new plot. So the voltage over your system is now pink. But let's look at the coil temperature, because not only you have the solenoid temperature now, not only the hotspot temperature, but also the solenoid temperature. And so once your switch is opened, your energy now goes into your solenoid, which is what we called our solenoid, our model. And then you do see a temperature rise. And this is basically what you would also get when you would perform this integral here. So when you look at the maximum temperature in the coil after quench, if you would dump all the energy inside it, you can do that by integrating over the volumetric heat capacity. And then if you take the stored energy of the coil and the volume, you can calculate this T max. And that's basically what you would see here as well. So that's internal dumping of your energy. That's the next case. Now, another quench protection method is not using energy extraction in any way, but by using heaters. And if you want to use heaters, there is quench heaters here. And basically here, what you need to set is a time at which a certain part of the coil, a certain percentage of your coil has quenched after switching in the heaters. So this is not a heater switch in any way. It is a switch. It's a time at which you know more or less X% of the coil has already quenched. And so for LTS, we can sort of say that at, I guess, 100 milliseconds, 80% of this coil will probably be quenched. So then it's also important to make sure that the protection voltage is set to 0, because otherwise it will assume that there's still a dump resistor or something like that in place. So if we set this to 0 and we keep this, we still have a switching time of when your power supply switches off. So this, in case you have an external resistor, it switches from the power supply to the resistor. So it's a switch that switches the resistor in series, but also turns off the power supply. But if you have 0 volts here for the protection voltage, it does still switch off the power supply, which is what you would normally do in case you have heaters only. And then it will take 0.1 second for this 80% of the coil to heat up. And so this is what you will see in the results. So if we look at the calculation, again, we use calculate to start. Again, the pink plot here is the protection is the voltage of the protection circuit. So you still have that the quench is detected, and then 0.03 seconds later, your protection switch starts to open, and then 0.03 seconds after that, it's actually open, and then your voltage goes to 0 because we don't have a protection resistor. But then it still takes a bit of time. You see here, there's a bit of time. This is the coil temperature, the solenoid temperature. After that, to reach this 80% quenched. So this is the time that you see here. And when 80% of the coil then is quenched, it then starts to calculate. Based on that, you have basically 80% of the coil resistive. Based on that, the power dissipation into the coil and what that means for the temperature of the coil. So that's this plot, but in the meantime also your hotspot temperature still rises until most of the current is out of the coil. That current is seen here, until most of the current is out of the coil, because then both temperatures start to stabilize. So here you now have a maximum hotspot temperature of about 120, a little over 120 Kelvin. Because you now use heaters instead of an external dump. So that's the case of using heaters only. Now the last case we want to discuss today is the use of, for instance, a support cylinder or any support structure that you can drive a current into, for instance. So I prepared already a support cylinder. So I don't know if you know about this feature, but you can enable and disable structures in your model. Right-clicking them, then there's this enable button. So that's what I just did. And because we want to use this for our quench simulation, we need to make sure that there's material assigned to it. So you can always right-click and add a material. In this case, we assigned a metal to it, aluminum 5083. That's this one, and that's used because once the coil is being discharged, a current will be able to will be inductively be induced into the support cylinder, and you will see that in the form of current and also the temperature rise, because this is a resistive material. So when there is a current going in here, it will warm up. But again, because it's an adiabatic model, you will not see any quench back happening from that. So the heat that is happening from the inductive current in the support cylinder will not be transferred to the coil, and so there will not be quench back visible. So in our support cylinder we have a circuit ID 2, which is important because we also need a circuit for our support cylinder. I'll call this one support, and here it automatically already added 2. But if it doesn't, then you need to make sure it is number 2, because that's the circuit ID for our support cylinder. Make sure you set it to 0, because there's no current in the support cylinder. And if we look at the quench detection, it should also be 0 volt for quench detection. In any case, it's a non-superconducting material, so it can't quench. But also the protection voltage should be 0, And then that's it, more or less. I changed these values now, but in principle you don't need to change them. You only need to make sure that the protection voltage and the detection voltage are 0. Because if we then look at the calculation results, we will not only see the current in the superconductor, so in the solenoid, but also in our support structure. So let's first look at the current. Actually, in fact, the voltage is still interesting. So we did use, what did we use? Actually, we used a resistor, a normal resistor in our normal circuit. So this is the circuit of our solenoid over here. So we set this to have 100 volts and the resistor is switched in. There's no heater, so the heater time is infinite. And there's still a bit of time delays due to signal processing and switching time. And once this is switched in, you see that a current is being driven in the support cylinder. That's this current. And because of that, your support cylinder also heats up. And that's the support temperature that you see over here. That's this one. You also see the hotspot temperature. That's the temperature in the coil of the hotspot. But because we use external extraction, we have a dump resistor. Again, the coil itself doesn't heat up. It would normally in real life, but there's no heat transfer. It would heat up because the heat transfer from the hotspot and the heat transfer from the support cylinder. The support cylinder only heats up because there's a current being driven into it inductively. But as soon as the current sort of is gone, so that's here, the change in current is smaller and smaller, so the current also in the support cylinder goes down and down again. There you go. So this is the last case that I wanted to discuss today. There's one thing I didn't actually discuss yet, and that is this parameter f-trans. And trans is basically the parameter that determines how fast your normal zone spreads in the transverse direction. So now for LTS, since it spreads very fast longitudinally, I didn't touch it, but if you have a HTS, or if you want to include transverse normal zone propagation, you can basically set this value, and what it then does, it calculates a spheroid, so the normal zone propagation length in the longitudinal direction is calculated by taking the normal zone propagation velocity times the time. That determines the length of the normal zone times 2, because it spreads in 2 directions. And the transverse normal zone propagation is basically 0.1 in this case times the normal zone propagation in the longitudinal direction. Then you have a spheroid for which you can calculate the volume. And if you know the volume of the area that has quenched, you can calculate the voltage. So this is what you can use to include transverse normal zone propagation, not only longitudinal. And this basically concludes our tutorial for today. Bye bye.